from the David MathWorks band. Our group members are Amin, Marcy, and Jacob. We selected the steganography project, which focuses on concealing messages or information within other non-secret text or data. Our project required us to embed and conceal 10 hidden images into a non-secret dog image. We began by flattening the images into a 400 by 400 matrix that relates to the pixel being white or black. The next step was to make a function to expand the image, which makes a new RGB. After that, we created embedding techniques to hide the black and white image in the dog image. For each embedding technique, we also will need to make a recovery technique to retrieve the hidden image. Then the final step is creating a GUI to allow the user to easily go through the process with buttons alone.
Hi, it's Marcy. So I'm just going to be going over the even-odd technique used to embed and recover our images. So as Jacob said, the first thing we need to do is flatten the image, changing its values into binary values. After that, our RGB needs to be expanded. Then we move into the actual embedding aspect of our technique, which assigns a value to our white pixels and our black pixels. And for this example, we've decided to make our white pixels correlating to an even value and the black pixels correlating to an odd value. After that, we embed our image, display it, and then we move on to the recovery aspect of our technique, which basically checks the pattern of odd pixels and reconstructs the hidden image using those values. So now we're going to go over the XOR method, which follows the exact same format as the other methods, at which time the image has to be flattened, the RGB needs to be expanded, and then when we move into our respective loops. So unlike the other ones, this method uses the XOR logic function to locate the pixels of the original image, where we will hide the secret image. Then the modified function identifies where the pixels of dog data are divisible by 5, at which time 4 is added to the value of the original image in order to recover the secret image.
Hi, my name is Amin, and I'm going to be talking about the three other methods of embedding, which is the shifting, the scaling, and then the switching. I'm going to start off by the first method, which is the shifting. So, which is down here. So the shifting method basically starts off by taking the user input, which is 3 selected images, and then it would flatten them out and expand them. After that, we're gonna go to the three first for loops, which will trace the location of the black pixels in the secret image, then shifts that location in the original image by a value of 2.5, which translates to changing the second least significant bit and so on, depending on the value of the original image. The recovery part basically traces back all the shifted values to construct the secret image and display it back. Now, for the scaling method, which is the second one, it starts off by flattening and expanding, and then the first 3 for loops will pretty much go and scale all the bits of each pixel, aligning with the location of black pixels in the secret image by a factor of 1.005, and then it would go and scale all the bits of each pixel aligning with the white location in the secret image by a factor of 1.002. After that, after all those pixels in the original image have been converted from an 8-bit integer value to values of double type. Then in the recovery part, it works the same way as the previous function. It traces back all the changed pixels aligning with the black pixel in the secret image and then recovers our secret image back. Then finally, for the shifting method, what it will do is switch the least digit of all pixels aligning with the location of black pixels in secret image to a value of 5, and then it will switch the location of white pixels in the secret image by a value of 10. which translates to changing a wide range of most bits of the dog image, depending on the original value of the pixel. The recovery method basically follows the same concept, which is tracing back all the pixels that were changed following the black pixels pattern in the secret image, and then constructing our secret image back. Thank you.
The David MathWorks band graphical user interface. We kept it real simple and easy using the buttons and 4 screens. So in order to use this, the first step will be to load the dog or cat image, whichever you choose. The next step will be to choose the secret image out of this line here, which secret image you would like to use. Let's go ahead and run the code so we can show you that. So here's the final upload. Now we have the dog. We'll load the dog image, for example, and then you can choose which image you want a secret image to hide. Once you choose your secret image, you select the first, second, and third secret image that you want. So let's start with 4 for the first secret image, 6 for the second, and 8 for the third. Now you're going to select your embedding method. So over here on the right side, we'll choose the shifting method to embed. Once you've done that, you click the embed, and it will embed all 3 hidden images at one time. This produces the embedded image that hides those 3 secret images into the one original image. After that, you can recover any image you want by selecting on the same graphical button, recover first image, second image, or third image. Start with the first, and the second, and the third.